Here we go. All right, so today we are going to be graphing rational functions. In the last unit, we solved rational functions. We simplified rational functions. You did a quiz on that. Today we are graphing rational functions. The parent function for rational functions is 1 over x. So in every rational function, you're going to have at least one x in the denominator. Before we talk about what the x and y intercepts are on the rational function, I want to talk about the asymptotes. Rational functions usually have both vertical and horizontal asymptotes. So the vertical asymptote is between these two branches, and I want you to make a dashed line on your y-axis here. The equation of that vertical asymptote is x equals 0. And they also have a horizontal asymptote between the two branches. And the equation of that is y equals 0. All right, because we have asymptotes on your axes, you don't have an x-intercept or a y-intercept. Now, once we start shifting this graph around, you will have x and y intercepts. So the parent function does not have them. The domain comes in two pieces. Notice how the graph has two pieces. You're going to have the domain of this piece, and then because there is this value in the middle that's not defined, we have to then separate and do the domain for this piece. So this piece starts over here at where x is approaching negative infinity. And it continues and gets really, really close to 0, but it doesn't touch 0. So we do 0 with a parentheses. That gets really close to 0, but doesn't touch it. And then I'm going to put a u for union. I don't actually care if you put the u there, if you leave it out, but you'll see them a lot, like especially if you're taking a standardized test. And then after that, we're going to do this piece. This piece starts right after 0. And then it goes to where x is approaching positive infinity. Like that. So you see your domain is just in two pieces. Your range is actually going to be the same in this case, but not always. So in this case, your range is going to start at the bottom. It's going to go up to 0, not including 0 because of the asymptote. And then the next piece starts right after 0, and it goes to positive infinity. So the same range in the parent function. All right, I want you to take a try at your end behavior. I'm going to give you the beginning of it. The right side is as x goes to positive infinity. You're going to fill in what does y go to. The left side is as x goes to negative infinity. And then you're going to say what the y goes to. All right, so take a stab at that one and then check with a neighbor and see if you got the same thing. As x approaches infinity, the y is decreasing. It's getting smaller and smaller. However, it does not go to negative infinity. As x goes to positive infinity, it's getting closer and closer to the asymptote, which is at what number? 0. As x approaches negative infinity, again, even though it keeps increasing, it's getting closer and closer to the asymptote, which is at what number? 0. Still 0. So this is a horizontal asymptote. Is not actually this magical line that you can't ever cross. This graph doesn't cross the horizontal asymptote, but we're going to get to a graph on our notes where it actually does. So there's nothing magical about not crossing the horizontal asymptote. The horizontal asymptote actually defines your end behavior. So anytime you have a horizontal asymptote, that number will be your end behavior. Okay? The vertical asymptote is an undefined value. You will not ever cross your vertical asymptote. So I want you to make a quick note to yourself about the horizontal asymptote. The horizontal asymptote is your end behavior. By definition, not by coincidence. Questions on that one? Okay. I'm going to talk to you about A, B, H, and K, and then you guys are going to name what the transformations are down here. You may remember A, H, and K from transforming other functions. Remember this one, the quadratic, right? Remember the H was left and right. What was the K? Up and down. Very good. And the A could do a lot of things. What's one thing that the A value could do? It could stretch it, yeah? What else could the A value do? Compress. And then if it's negative, reflects. Okay. So those are all the same. We have a B value here. I'm not actually sure why we put it in our notes because we don't really use it in Algebra 2. Like you could use it for sure. But in Algebra 2, we just don't go that deep into transformations. But I'll tell you what it is anyway. So the A is the vertical stretch compress or reflect. All right, the K is also vertical, and that is the shift up and down. Now the things that are with the X, those are things that happen to the X, so they happen horizontally. And just like the X minus H actually moves you to the right, the B value here is also going to work inversely. We'll talk about that in a second. Let's do the H first, because we know the H is going to shift you left and right. And remember, it's backwards from what you think, so if it's a plus, it's actually left. The same thing with the B value. The B value is a horizontal stretch, compression, or reflect, and it also happens inversely. So if the B value was like 0.5, it would actually stretch you horizontally instead of compress you. All right, we're not going to be applying B values in our notes or in our practice, but just so you know, you'll get to it later if you do a pre-calculus course. This one is horizontal. Stretch, compress, reflect, and also happens backwards. And also it's backwards. Okay, so I'm going to check in with people while you guys are doing this. You're identifying the transformations in example 1. Okay, transformations. Raise your hand if you can name one of them. Let's just do one at a time. I would like some volunteers. All right, looking around for some volunteers. Dylan, what's one of them? Shift up 4, good. If you're missing that one, add it in. All right, raise your hand if you got another one. Sal?
Shift right 1.
Shift right 1. If you're missing that one, add it in. Henry, you got another one for us?
A vertical stretch of -2.
Okay.
A vertical stretch.
Yeah, vertical stretch of 2. Good. Vertical stretch of 2. And then he was noticing that there's also a negative on that. What does the negative do? Reflects, right. So I'll just move that over here. Vertically reflect. Okay. So if we're just imagining for a moment what this graph might look like, think about these asymptotes being shifted left, right, up, and down, okay? So my vertical asymptote is going to shift right 1. My horizontal asymptote is going to shift up 4. The stretch is like kind of hard to see in the graph. We're going to have to probably use some points to get to see what the stretch looks like. And then the reflection is going to do this. This branch will flip down here, and then this branch will flip up here. What I'd like to do is first graph the asymptotes, and then we're going to graph this in the calculator to see what the rest of the points look like. So for my asymptotes, we said the shift up 4 takes your horizontal asymptote from 0, and it shifts you up 4 to y equals 4. 1, 2, 3, 4. All right, we know that because of the plus 4. That was exactly the same thing when we graphed exponential functions. All right, then the shift right 1 is going to shift your vertical asymptote from 0 to x equals 1. All right, so to get our branches in the right place, we're going to make a table of values. We'll get it from your graphing calculator in just a moment. But here's something important to know. We want numbers on the left of the vertical asymptote and also on the right of the vertical asymptote. So I'm just going to choose the two values before and the two values after the asymptote. So before 1 is -1 and 0. And then after 1 is 2 and 3. And that way I'll have 2 points on each branch. When you graph it in the calculator, you will need to use parentheses to keep this denominator together. All right, so press the y equals button on your calculator. And then let's graph your function. Remember the parentheses. Oops, I don't need that one. -2 divided by x minus 1. Plus 4. Okay, so y equals button is top left. Often it is completely worn off. You can press the graph button to see what the graph looks like. But what's going to be really helpful is second graph, because that's going to give you the table. And you're going to copy down your values for y. So when x is -1, y is 5. And when x is 0, y is 6. When x is 2, y is 2. And when x is 3, y is 3. All right. I saw some of you guys sketched in branches, but your branches need to have these points on them. So you're going to graph -1, 5. I feel like that's wrong. -1, 5. Is that right? Because why is it not oh, it did reflect. The bottom one went up there. Okay. -1, 5. And then 0, 6. And then you can sketch the branch through those points. Remember that the idea is that you are getting closer and closer and closer to the asymptote. It is really hard to draw that, but just do your best. Next one, 2, 2, and 3, 3. Okay, and then you should be getting really close to your asymptote. I understand that it's really hard to do that. Let me show you what not to do though, please. Don't do something weird where they come in like this, like that. It's not that. That's getting farther from your asymptote. You should be trying to get closer to your asymptote, okay? So don't do that. Also, it's not a function because it doesn't pass the vertical line test. Okay, domain. 2 pieces. -infinity up until your vertical asymptote at 1. And then 1 to infinity. Raise your hand if you had your domain correct. Raise your hand if you have a question about the domain. Okay. Range is going to start down here, -infinity, and it goes up to the 4. Then after the 4, it's going to go up to positive infinity. Just as an aside, I'm going to show you another way that people write this domain or range, but I want you guys to use this method, okay? Another way people would write this domain is they would write all real numbers except not 1. So if you saw this, you with me? Okay. If you saw this, it means the same as this. For the range, they would write all real numbers. This time, remember, range is y, not x. Y does not equal 4. So I want you to understand that if you see it, but I want you to use this method. Okay, x-intercept and y-intercept. I already have the y-intercept in my table of values. It's right here, 0, 6. Sometimes you can just see this as an integer for your x-intercept. Yesterday I was trying to solve it algebraically and it wasn't working out, but I think it's worth a try. We're going to try it real quick. For your x-intercept, you make y equal to what? 0, yeah. So it would be 0 equals -2 over x minus 1 plus 4. And then you subtract the 4. My goodness. And then to get your x minus 1 out of the denominator, you can multiply by x minus 1 on both sides. There's hardly room to do that here, x minus 1. That would cancel that. This will distribute. -4x plus 4 equals -2. Subtract the 4. -4x equals -6, and then divide. And we get x equals 1.5. I want you to remember you can also calculate that on your calculator. You should not have to do something that long in order to solve, but you should be able to do it if you have to. So your x-intercept is 1.50. I'm going to set up your end behavior for you, and I want you guys to fill it in. As x goes to infinity, y goes to something. As x goes to -infinity, y goes to something. Both end behaviors are 4. If you didn't know that, make this note, please. The horizontal asymptote is your end behavior. The horizontal asymptote is your end behavior. So you should have 4 here and here. When you're ready, turn the page. Okay. This is a different format of rational equation. It's not based on transformations, but we still need to know how to graph it. Right. This is a different format. Notice that you have an A value and a C value, a B value and a D value, and these are totally different things from the previous slide. So we cannot graph this with transformations, but we still need to know where your asymptotes are. All right, the easier one is the vertical asymptotes. The vertical asymptotes are anything that makes your denominator 0. So for this one, for your vertical asymptote, you're going to take your denominator of x minus 4, set it equal to 0, because remember you can't have a denominator of 0, and so that's going to tell you what value is undefined. Add the 4 and get x equals 4. So your vertical asymptote is x equals 4. That's the easier one. The horizontal asymptote has a somewhat complicated set of rules. And it depends on the degree of the numerator and the degree of the denominator. So let's think about, for a moment, a function. I'm just going to make one up. Okay. As x goes to infinity, quiet please. As x goes to infinity, which of these terms is the most important? Infinity to the 3, infinity to the 2, or just the plain old infinity? Which one is going to affect your graph the most? Infinity to the 3, right? Because that's infinity cubed. That's like the biggest infinity of all of the infinities here. This one is going to be the most important. sometimes it's hard to think about infinity cubes. So you could think about a big number like 1,000,000, right? 1,000,000 cubed is much bigger than 1,000,000 squared and much bigger than 1,000,000. So this is the most important one. So when you have polynomial on the top and on the bottom, these are the ones that are going to matter at the end. Just these, okay? Now, you've got infinity to the third over infinity to the fourth. Which one's bigger? Infinity to the fourth is bigger, right? So if you've got a fraction where the top is small and the bottom is big, right? What number is that really close to? Think about like 1 over 1,000,000. What number is that really close to? 1 over 1,000,000 is not close to 1. It's a good try though.
-50. Hell.
Why don't you type 1 divided by 1,000,000 in your calculator? 0. It's really close to 0. Yes. All right. So this number here, the thing that's important is the leading one, right? The bottom's much bigger, so this number is very close to 0. Now I'm trying to explain to you why these rules work, but now I'm going to tell you what the rules are. When the degree of the top is much bigger than the degree of the bottom, your horizontal asymptote is y equals 0. So we're talking about the degree. Thank you. Just grab those notes. You actually sit back there, but you can take those notes. All right, so this one is the bottom has a bigger degree. This one is if the top has a bigger degree and there's no horizontal asymptote in that case. And this one is the same degree on top and bottom. Okay, so we're going to look at our example here. In our example, the degree is the largest exponent. If your x's don't have an exponent, then what number is that? 1. It's x to the 1. So I have 3x to the 1 over 1x to the 1. Is the bottom bigger? Is it same degree? Or is the top bigger? Same, yeah. They're the same degree. They're both 1. So then it says a over c. A is the coefficient on the top, and then c is the coefficient on the bottom. So this one has a coefficient of 1. So it's y equals 3 over 1, which becomes y equals 3. I get that that's complicated. First, we had to figure out what type of horizontal asymptote it was going to be, and then we had to find that ratio of the least coefficients. So we're going to put those in. So your vertical asymptote is at x equals 4, so 1, 2, 3, 4. Your horizontal asymptote is at y equals 3. Like that. And then we're going to use a calculator to help us get some points. You do need parentheses to keep your numerator and your denominator together. And I'm going to choose x values on both sides of my vertical asymptote. So before 4, I could choose 2 and 3. And then after 4, I could choose 5 and 6. All right, take a moment, graph this in your calculator, look at your table of values, and then get your points on your graph. If you haven't graphed it yet, you should press the y equals button and graph it right now. You can take a look at the graph to see what it should look like, but what you really need is the table. And I'm going to copy the y values for x equals 2, for x equals 3, for x equals 5, and then I need to scroll down to see when x equals 9. No, sorry, I want to see when x equals 6. 6, 6, okay. And then you want to graph those points on your paper. Oh, okay, let me take a look again.
But mine is like weird.
So let's look at your y equals. Do you have parentheses before and after the numerator? Okay. And then before and after the denominator?
I have it on the
Okay. Yeah, anytime you have more than one term, you'll need parentheses. Okay, so 2, 0, 3, negative 3, 5, 9, and 6, 6. Oops, I think 5, 9 is actually up here. You know what, and just because I know I need to know what my y-intercept is, I'm going to find my y-intercept as well. So second table, 0, 1.5. So I just found that on the table, 0, comma 1.5. All right, your domain is going to be negative infinity up to 4. And then also 4 to infinity. Your range is negative infinity up to 3. And then 3 to infinity. Your x-intercept was in your table of values. Remember where y is 0, x is 2? So you didn't have to do any work to find that. And then your end behavior is going to have x going to positive infinity and x going to negative infinity. And your end behavior is your what? Your end behavior is your horizontal asymptote. Excellent work. So it's going to be, in this case, 3, right? Okay. Who has a question on that one? Because I'm ready to start example 3. Example 3 is interesting. It's a little bit different. Here, I'll zoom a little bit. Zoom. Do you guys remember, how do we find our vertical asymptote? We set what equal to 0? The bottom, yes. So for your vertical asymptote, we're going to do x squared minus 9 equals 0. Take a moment and tell your partners how we would solve that quadratic equation. All right. We're going to factor it. It's difference of squares. Difference of squares is that plus minus pattern. I did hear somebody say solve it by square root. There is a way to do that. You would have to add the 9 to both sides, and when you square root it, you have to remember your plus or minus. But everybody always forgets the plus or minus. So let's do the factor. You got a plus, and you got a minus, right? And then it's going to be x plus what number? 3, good, because 3 is the square root of 9, and then x minus 3. And then you set each factor equal to 0. And then we'll subtract here, so we'll get x equals negative 3. And we'll get x equals positive 3. All right, now we did all that to find the vertical asymptote. What does this mean? There's 2 vertical asymptotes. You can have 2 vertical asymptotes. You can actually have 10 vertical asymptotes. There is no limit to the number of vertical asymptotes you can have in a function. However, in this class, we probably won't have more than 2. Okay? So x equals negative 3, x equals 3, 2 different ones. And so we make a vertical asymptote at each of them. Your horizontal asymptote, depends on the degrees of the numerator and the denominator. So what is the degree of the numerator? I just gave you a hint. What's the degree of the numerator? 1. Yeah. And then what's the degree of the denominator? 2. So, which has a bigger degree, the top or the bottom? Bottom. So the bottom is bigger. Take a look at our notes up here. If the bottom has a bigger degree, your horizontal asymptote is y equals 0. Make sure you understand where that came from. If the bottom has a bigger degree, your horizontal asymptote is y equals 0. Okay, I am going to need points on all 3 branches. I'm going to need points here, here, and here. So I'm going to graph this in my calculator. I am going to put parentheses, at least on the denominator. It does not hurt to put it on the numerator too. When you put this in your calculator, the values I want you to grab are before -3, so we'll do -5, -4. In the middle here, I'm actually going to do 3, -1, 0, and 1. And then after the 3, we'll do 4 and 5. So that's a lot of values for you to grab from the table. So put that in your calculator, look at the graph, and then I want you to put these values in your table. All right, when you graphed it on your calculator, does it look like that? Okay. All right, so I'm going to get my table of values now. I'm going to press second table and see if I get what you got. You have to go back to -5. So -1.25, -2.3, 0.5, 0, -0.5, 2.3, and 1.25. All right, so if you haven't graphed it yet, let's do this now. I have to go back 3, 4, 5, and then -1.25. Go back -4, and then -2.3. -1.5, 0, 0, 1, -0.5. 4, 2.3, and 5, 1.25, like that. All right, raise your hand if you can tell me something interesting about this graph. Anything that you notice about this graph. How could you be wrong? Just raise your hand and give an answer, right? Anything that you notice about this graph, raise your hand. There's 3, yeah. And those, the name for those are branches, the branches of the rational function. 3 branches, excellent. Raise your hand if you notice something different. Anybody notice anything different? Did you guys see that we crossed the horizontal asymptote? It's exciting, we crossed the horizontal asymptote. Some people think like you can't cross the horizontal asymptote, but you can. You just can't cross the vertical asymptote, okay? Because we crossed that horizontal asymptote, our range has only one piece. You see that? Because we have to include the value of the horizontal asymptote because we crossed it. So your range is interestingly only going to be -infinity to +infinity. All right? Just one piece for your range. How many pieces does your domain have? 3 pieces in your domain. I'm going to switch to my smaller pen so I can fit this in. So your domain is -infinity to -3. -3 to +3, and then 3 to infinity. Okay, so your domain had 3 different pieces, but because we crossed the asymptote, your range has just one piece. Your x-intercept and your y-intercept are the same point, which is what? 0, 0. Okay, end behavior is just about the ends of the graph. All of that foolishness in the middle of the graph does not affect your end behavior. End behavior has nothing to do with this. All we care about is the left side and the right side. And on the left side, the y value is approaching what? So the x is going to negative infinity, right? And the y is approaching your horizontal asymptote, which is what number? 0. Good. And on the right side, same thing. As x approaches infinity, your y is still approaching your horizontal asymptote. So your horizontal asymptote will always be your end behavior.